Welcome to your second lesson in Chapter 12. And in Lesson 1, we talked about evaluating limits graphically. This time we're going to evaluate them algebraically. Algebraically. I have typed up a lot of the different limits for you, and so you don't have to copy those out of the book or in the notes. But I do want to talk about them, and we're going to go through and identify them. So if you let C be any real number, and n is a positive integer, if you take the limit as x approaches the real number of a constant, it's going to equal that constant. And we call this identity the constant identity. Real original, I know. This one, as x approaches that real number of the function x, it equals the identical value. So we call this the identity property. Identity. There we go. This one has a k value that's in with the function, and you can pull that out front. And that becomes, it's a multiple out front. We call that the scalar multiple. You also can have a sum or a difference, and I kind of wimped out on this one and put them both in the same equation. So if you have two functions, you're taking the limit of two functions that are added together, you can split that up and take the function of the first one plus the function of the second one and the difference as well. So we're going to call this just the sum and the difference property. This one, if they're multiplied, you have the product, and you can, again, split that up. So you're taking the limit of one times the limit of the second one. Okay, so you can split it up if you want to, and this one is appropriately named the product property. This one, if you're dividing, you can take the limit of each one. Now, because you're dividing and you're creating this rational function here, the limit of the denominator of the g function cannot equal 0. But we, of course, call that the quotient property. This one here, if you have an exponent, you have the function raised to the power of n. You can take the limit of the function and then raise that to the power. That's called the power property. I'm never going to ask you these names, but sometimes they're referred. You refer to them in a problem or such, and I wanted you to have the names. And it's a good review of the different properties. This one is called the nth root, appropriately named as well. Now when you get down here, I kind of blocked these off a little bit. These deal with identity. These are limits of functions at infinity. At infinity. So this is at infinity as x approaches infinity. This is as x is approaching negative infinity. It changes depending upon if the n, the exponent, is odd or even, and that makes sense. If you have an even exponent, then as it's approaching negative infinity, it's going to change that to a positive infinity. If it has a negative or an odd exponent, then as you approach a negative infinity, it would still remain negative. So these are limits of functions at infinity and negative infinity. I'm going to scoot this up a little bit. Now we're going to also talk about polynomial functions. So if C again is a real number and p of x and qx are polynomial functions, then as you take the limit as x approaches c of the polynomial function is just that function at c. You notice you just plug in that value. Well, that's kind of what you've been doing on some of your problems, but this is the theoretical explanation. Here, if you have a rational function, and you can, remember from the quotient, you could take the limit of each one, but as you take the limit of this rational function, that is the limit of the function at c. And so you would plug in c in both the numerator and the denominator. Again, remember that c cannot be 0 because it's down here in your denominator. 15. When x approaches infinity of the polynomial function, that is equal to the limit of this term. Now this term you've seen before. That is the highest exponent degree of this polynomial. So when the polynomial is this x, the highest exponent, okay, so I'm just going to write that in here. This is the highest, and we'll do an example of this in a few minutes. Exponent. If you take the limit as x approaches negative infinity, it's the same thing. You also just are taking the first term. So essentially, when you have this polynomial here, you're ignoring the rest of the equation, and you are only taking the limit of the first term. It's kind of nice. And the reason is because you're going to infinity, all the rest of them are going to drop off. They're going to become so small, it's not going to really matter. So you're only playing with the first term. I need to add one more, and this one's kind of fun. But if you want to take the limit as x approaches infinity of the reciprocal function, that is equal to 0. Now it doesn't matter whether you come to x or 1 or negative, I did that again, infinity or negative infinity. It's still going to be 0. And we can expand that even further to say if it's 1 over x to a power. That will always go as a limit. As you approach infinity or negative infinity, it always approaches 0. That will come in handy as well. So I may, while we're doing different examples here, I may refer to some of these properties 1 through 16. And you can go back and make reference to these. You will never have to spit them back and give them to me. You just need to be able to utilize them and be very familiar with them. Okay, I'm going to pause while we get ready for some examples. Let me, before we jump into the examples, let me say that you can also solve these graphically like we did in section 12.1 if you would like to, but we are again giving you more tools, more ways to solve these. So the first one, let's use some of our properties to solve the limit as x approaches 2 of negative x cubed plus 4. So this is a sum, or I guess a difference if I flip the order around, but I'm going to go ahead and take this, I'm going to split this up into 2. So I'm going to say that's equal to the limit as x approaches 2 of negative x cubed plus the limit as x approaches 2 of 4. Well, here you can do the direct substitution if you wanted to, but if I plug in 2 here, I'm going to have negative 2 cubed. And if I plug that in graphically, you know the graph of a cubic function. And if it's negative, you would understand if you're approaching 2, you know that you are going to approach a negative 8. Because remember, that would start high and go low. So that would give me a negative 8 plus, if I take the limit of a constant, remember it equals the constant. So that would be 4. Negative 8 plus 4 gives me negative 4. That is my answer. Let's try the next one using direct substitution. The limit as x approaches negative 5 of this rational function here. So I am going to evaluate this. I'm going to plug in negative 5 plus 1 and negative 5 squared plus 3. So that gives me negative 5 plus 1 is usually negative 4. That gives me a positive 25 plus 3 is 28. Simplify, negative 4 over 28 is negative 1/7. And again, you can verify these by graphing them if you so choose. Some of your exercises will ask you to solve using factoring. And you will recognize some of the, whether they're quadratic, cubic, functions that you can factor. Now you get to something like this and you can't readily factor the numerator easily, but you really hope that there's one of those factors in that cubic equation. So let's try. You have the tools. Let's see if it divides evenly. So I'm going to go ahead and take x plus 2 and I'm going to divide it into x cubed minus 3x squared minus 4x plus 12. And I'm just going to quickly do this division and see if it works. Remember this long division? So that's x squared. So I have x squared plus 2x squared. You subtract, and you change the signs, remember? So here I'm really adding a negative and a negative, so that gives me negative 5x squared. I bring down the 4x. So my next term needs to be a negative 5x because I need negative 5x squared. So then I distribute that times both of these. That gives me negative 5x squared. And this will give me a negative 10x. Again, you subtract. Again, you change the signs. And now I'm going to have, that would go to 0, and now I'm going to have 6x. Bring down the 12, and look at there. If I multiply that by 6, then I perfectly get 6x plus 12, and I get 0. So I know that I can factor that. I'm going to rewrite this as x plus 2 times, both of these then, right here, are perfect factors for that polynomial. X squared minus 5x plus 6 over my x plus 2. So when you're factoring, now I can cancel those, and now I can do the direct substitution if you'd like, and we're taking the limit as x approaches negative 2. So now I can plug in negative 2, and I have negative 2 squared minus 5 times negative 2 plus 6. Well, that's 4 plus 10 plus 6. That is 20. And that is my limit. And again, you want to verify this graphically? You can. All right, I'm going to set up a couple more examples. But we're going to use rationalization here when we have this limit. So we're going to take the limit as x approaches 0 of 2 minus the square root quantity of x plus 4 divided by x. Now normally you think of rationalizing something that has a radical in the denominator and that you would have to get rid of. But sometimes you can rationalize from the numerator. And that's what we're going to do in this case. So if I want to rationalize and get rid of that radical, I'm going to multiply it by 2 plus square root of x plus 4 over 2 plus square root of x plus 4. See, I'm not changing the value of this right here because I'm multiplying by 1. It just looks different. Now when I distribute and FOIL my numerator, I'm going to have 4 minus x plus 4, correct? Divided by, down here I'm going to leave the x outside. I'll show you why in just a second. Square root of x plus 4. Don't distribute it yet. Look at what happens in your numerator. In your numerator here, that negative distributes, and you're going to have 4 minus x minus 4. Well, that's going to give you a negative x. So you will have negative x over x times 2 plus the square root of x plus 4. Now those x's do cancel, and you now have a negative 1 in the numerator. Don't forget that. You have a negative 1 over, and now we're going to go ahead and plug in the 0. So I have 2 plus the square root of 0 plus 4, and that gives me square root of 4, which is 2 plus 2. I have an answer of negative 1/4. Now we have 2 more examples that we'll do in the next video, and so the next video should be pretty short. And we'll come back and we will play with infinity in the next. Thank you.